Here we are going to discuss sets of linear combinations of vectors in a vector space. First, we consider a remark about linear combinations. So, given a vector space, if a vector v is a linear combination of vectors v1, v2 up to vk, then note that v is also a linear combination of vectors from v1, v2 up to vk, vk plus 1, vn. Meaning, v is also a linear combination of vectors from a larger set containing the given v1, v2 up to vk. This is because you can just append these guys with zero weight, with zero scalars. And more precisely, if you have sets S and T of vectors from V such that S is contained in T and V is a linear combination of elements of S, then V must be a linear combination of elements of T. However, it is not necessarily true that if S is a subset of T and V is a linear combination of elements of the larger set, then V is also a linear combination of elements of S. Okay, that's not necessarily true. If V sub 1 and V sub 2 are linear combinations of vectors from a set S, then by definition of vector addition, the sum v1 plus v2 will also be a linear combination of vectors from S. And finally, if v1 is a linear combination of vectors from a set S, then for any scalar r, the scalar multiple of v by r is also a linear combination of vectors from S. So given a vector space V and a non-empty set S of vectors from V, and the last two remarks imply that this collection of all linear combinations of vectors in S satisfies the two conditions in the subspace test. Of course, it is clear that this is a non-empty set because it contains the zero vector. If you take R1, R2, and up to Rk all equal to 0, then this linear combination will just be the zero vector. So this is a subspace of V. And we have a special name for this subspace. The subspace above, consisting of all linear combinations of elements of S, is called the span of S, or the span of the vectors v1, v2 up to v sub k. Or we will also call it the subspace spanned by the set S. And the span of S will be denoted either by this span parentheses S close to parentheses, or span of the set v1, v2 up to vk. Also follows from a previous remark that if V is a vector space and S and T are non-empty subsets of V with S contained in T, then an element of the span of S is also an element of the span of T. Now, some examples. In the previous video, we saw that 4, 2, negative 6 is a linear combination of the vectors this, and this. And uh, one linear combination relation you can provide is with scalars negative 2, 6, and 0 respectively for this device. So by definition, 4 to negative 6 belongs to the span of these three vectors. So take a moment to internalize how we express, okay, being an element of the span. Okay? So we use the symbol to mean that this belongs to this set. Okay? Look at how we use curly braces because we are referring to the set containing these three vectors. So moving on, and in the last video, we also show that negative 1, 2, 3 cannot or is not a linear combination of 4 to negative 3, 2, 1, negative 2, and negative 2, negative 1, 0. And so, we write this to mean that negative 1, 2, 3 is not in the span of this set of vectors. Given a non-empty set S of vectors in a vector space, we'll say that S spans V, or V is spanned by S if every vector in V can be expressed as a linear combination of the vectors in S rather. So take a look at that direction. In this case, we refer to S as a spanning set for V. A spanning set for a vector space is just a set of vectors. Usually, we want this set to be simple and takes very few elements, has very few elements. That is enough to generate all the elements, all the vectors in V. So the definition tells us that set S is a spanning set for V if and only if the subspace spanned by S is precisely the vector space. Okay? So every element in V is a linear combination of elements of S. And taking all linear combinations of elements from S will produce all the vectors in V. Okay, since most vector space that we will study have infinitely many elements, having a spanning set with finitely many elements will be convenient for computations involving vectors in V. So when does a vector, or when does a set of vectors span V? The following algorithm describes a way to answering this question. So to check if a set of vectors spans V, first we take an arbitrary vector in V. And by this, we note that the step may include some arbitrary constants. Okay, so the keyword here is arbitrary. Arbitrary constants. So with B arbitrary, we want to know if B is in the span of S. That's obtained by solving, that's done by solving the equation 1 as shown, which as we saw no, in the last slide, in the last video rather, uh, translates no, to a linear system. So we can solve it by Gauss-Jordan. So V is in the span of S if and only if V is a linear combination of elements of S, and this means if and only if this equation has a solution. Okay, let's illustrate the idea. Let's consider a simple example first. So in R2, we verify whether or not S spans R2. Is it enough, no, to or for vectors 1, 2 to and negative 1, 3 to generate no, the entire Cartesian plane R2. So we take an arbitrary vector in R2. So see x, y are the components. So you want to check if x, y is in the span of S, and that's equivalent to finding real numbers R1, R2 that makes this equation true. In other words, xy equals the product of this 2 by 2 matrix with this 2 by 1 matrix. Well, this is just a 2 by 2 matrix, so actually we can proceed by making use of the inverse, okay, if it exists. You can just observe that the determinant of this matrix is non-zero. The determinant is 3 minus negative 2, 5, or which tells us that the system has a unique solution. It comes from the non-singularity of the coefficient matrix. So as I said earlier, if we multiply both sides by the inverse of the coefficient matrix, then we get R1, R2 equals this. And this expression no, is obtained using a remark no, about the inverse of a 2 by 2 matrix. Essentially, you just multiply by the reciprocal of the determinant, then interchange 1, 3, then interchange the signs. No? Change the signs of the 1, 2, and 2, 1, and 3. So that's how we got this matrix here, which upon multiplying to the vector xy gives this expression. So R1 equals this, R2 equals this. Okay. So we use this solution because we're just dealing with the 2 by 2 coefficient matrix. Okay. And yeah, so any vector, this tells us that any vector xy in R2 can be written as shown. Okay, xy equals R1 times this plus R2 times this, but R1 from our solution above can be written in terms of x and y, and the same is true for R2. Now, because x and y is arbitrary, rather, because the vector xy is arbitrary, we conclude that the span of S equals R2, or S spans R2. let's do another example. So in the same vector space R2, consider the set T with elements as shown. Does this set span R2? So again, we take an arbitrary vector in R2. We have to check whether or not xy is a linear combination of these vectors. But indeed, this is a linear combination of the three because xy, this vector xy, can be written as the scalar multiple of 1, 0 by x plus the scalar multiple of 0, 1 by y plus the scalar multiple of 1, 2 by 0. Okay, so this shows that T spans R2, or span of T equals R2. So the two examples show that there may be several spanning sets for a given vector space. R2 can be spanned by the vector S here, 1, 2, negative 1, 3, with only two elements. And R2 can also be spanned by this vector T with three elements. Okay. Final example. So in R3, this time the vector space is R3. Consider W with elements as shown. So does it span R3? Well, we apply the algorithm. So we take an arbitrary vector in the mother vector space, say ABC. Then, by definition, this arbitrary vector is in the span of W if we can find real numbers R1, R2, making this equation true. Okay? In other words, if this linear system has a solution. Okay? So consider the augmented matrix of this system and apply Gauss-Jordan process. So these elementary operations will turn our augmented matrix into this guy. Now remember that we used an arbitrary vector from R3. And the values of A, B, and C affects the consistency of the linear system. So as in this last augmented matrix, we see that the system is consistent if and only if this entry here is 0. Okay? Well, this is consistent if and only if the rank of the augmented matrix equals the rank of the coefficient matrix. Since the rank of the coefficient matrix is 2, consistency requires the augmented matrix to have rank 2. And that is equivalent to forcing this entry to be 0. Okay. So this shows that the elements of the span of this set of vectors, okay, the elements of the span of this set of vectors are the triples, okay, the triples whose third component equals the negative of the first component. Okay. C equals negative 8 from this equation. For instance, if you take A and B both equal to 1, and 1, 1, negative 1 is in the span of W, but the vector 1, 1, 1 is not in the span of W because the third component is not the negative of the first component. So there are some vectors in R3 that do not belong to the span of W. In other words, W does not span R3. not all elements of R3 is a linear combination of vectors from W.